You know, when you drive past one of those huge industrial plants with all the pipes and towers looking like some kind of metal city, have you ever wondered what's keeping all of that from, well, going boom? It's a question of immense pressure, in every sense of the word. So let's really ask that question. What is it that keeps all that incredible pressure safely locked inside? The answer isn't just one thing. It's a whole discipline of engineering built on understanding what can go wrong so you can design systems to prevent it. And the main threat they're always worried about is something called overpressure. The easiest way to think about it is like a kitchen pressure cooker. It's made to handle high pressure, right? But if that little safety valve on top gets clogged, the pressure just builds and builds until the whole pot can literally fail. Now imagine that on an industrial scale. That's overpressure, when the pressure inside a piece of equipment goes beyond what it was designed to handle, creating a massive risk of failure. So in this explainer, we're going to dive into how engineers tackle this pressure cooker problem. We'll look at what happens when good equipment goes bad. We'll cover threats that come from the outside. Then we'll get into how they design against disaster. And finally, we'll talk about the safety bottom line. Okay, first up, let's talk about the problems that can pop up from inside the system itself. This is what happens when good equipment, well, goes bad. To get a handle on all this, engineers usually sort these internal risks into four main categories. You've got your blocked outlets, which we'll get to in a second. Then there are failures in the control systems. Third, you have the really dangerous entry of a volatile material. And fourth is the potential for a runaway chemical reaction, which is exactly as bad as it sounds. And what's kind of wild is how simple the cause can be. One of the most common issues is just a blocked outlet. It could be a clogged pipe, sure, but a lot of the time it's just a single valve that someone accidentally closed. If you've still got a pump pushing liquid into that pipe, well, that closed valve just turned it into a pressure trap. The pressure has nowhere to go but up, and it goes up fast.
Now, modern plants are super automated, but those automatic systems can fail too. For instance, an inlet valve could get stuck open, just flooding a vessel. Or the opposite could happen. An outlet valve fails closed, and boom, you've got another blocked outlet. Or maybe the problem is with the brains of the operation. A sensor fails and starts sending junk data, tricking the whole control system into doing the exact wrong thing. But see, those scenarios often build pressure over a little bit of time. There's a much more violent, much more immediate threat that can happen. And that's when a volatile material, like plain old water, suddenly gets into a vessel that's filled with a much, much hotter fluid, like oil.
And the danger here is just extreme. The industry's own safety standard calls these things superheat limit explosions. It actually says, and I'm quoting here, that the timeframe is analogous to a detonation. That instant flash of water into steam creates shockwaves. It's so fast, so explosive, that your standard pressure relief valve is completely useless against it.
Okay, so that's the stuff that can go wrong on the inside. But what about when the danger comes from the outside world? That brings us to our next section, threats from the outside. The number one external cause, the one that engineers spend the most time analyzing and designing for, is an external fire. If you get a spill of flammable liquid and it ignites, those flames can just engulf the nearby equipment. As the fire heats up a vessel, the liquid inside starts to boil and expand, creating a huge amount of vapor and sending the pressure skyrocketing. This is where a tool like this comes in. It helps engineers do the math. They can plot out all the variables, temperature, pressure, the type of liquid, and figure out exactly how much vapor that fire is going to create. And that calculation is absolutely critical because it tells them how big the safety valve needs to be to vent all that pressure safely. Another really big external threat is utility failure, like a total power outage. A blackout isn't just one problem, it's a domino effect. Suddenly you lose the pumps for cooling, the fans on your air coolers, your compressors, and even the instrumentation and control valves. In a single instant, multiple layers of safety just vanish. So, you've got all these potential failures lurking: blocked valves, power outages, fires. How in the world do you build a system that can handle it all? Well, that brings us to the core philosophy for all of this: designing against disaster. Here's the thing, engineers have to be realistic. You can't design a system to survive every bad thing happening at the exact same moment. It would be impossibly complex and expensive. So instead, they rely on this foundational design principle they call single jeopardy.
The idea is that the entire safety system is built to handle one single, credible, and unrelated thing going wrong at a time. So an engineer will absolutely design for a power failure, or they'll design for an external fire, but they won't design for a power failure and an external fire happening at the same time for two totally separate reasons. That scenario is called double jeopardy. And because the odds of two independent disasters happening at once are so incredibly low, it's not considered a reasonable basis for design.
And that right there is the core of it. The goal is to make the system tough enough to fully protect a piece of equipment during any single credible overpressure event. It keeps things incredibly safe without trying to engineer for scenarios that are just astronomically improbable.
So let's pull all this together. What's the safety bottom line? Why does this systematic way of thinking matter so much?
It really all comes back to this. By systematically going through every one of these credible causes for overpressure, both inside and out, engineers can design and build systems that can handle them. And these aren't just lines on a blueprint. These are the pressure relief systems that protect the lives of workers, the public who live nearby, and the environment itself.
And that leaves us with a final thought to chew on. If these gigantic, incredibly complex industrial plants build their entire safety philosophy on handling one major failure at a time, what does that teach us about how we should be managing risk in any complex system, whether that's in finance or technology or heck, even in our own day-to-day lives?